Hi, my name is Mike Gashler. I do research in artificial neural networks. I'm currently an associate professor at the University of Arkansas. Today, I'd like to share a few thoughts with you about turning large language models into cognitive architectures. Let's begin with a few definitions to make sure we're on the same page. So AI stands for artificial intelligence. In general, artificial intelligence is a rather practical domain. It tends to focus on seeking state-of-the-art methods for solving challenging problems. It's also a fairly objective domain of study, by which I mean it's all about the measurements. In artificial intelligence, it doesn't matter how long you've been studying or how many degrees you have. All that matters is how much accuracy you can obtain. Now, AGI stands for Artificial General Intelligence. It focuses on topics that are a little more in the domain of science fiction or the far future. People that are interested in AGI are often more concerned about the societal impacts, the safety concerns, or how humans are going to interact with robots. In general, these things tend to be more subjective, more difficult to measure. Now, cognition is the process of learning and making decisions. Essentially, it's what the brain does. And cognitive architectures are essentially blueprints for a machine that attempts to implement cognition. Cognitive architectures are still very theoretical because we don't know exactly how to do it. But it seeks to construct a machine that can implement specific cognitive abilities that have been identified in psychology or neuroscience. So cognitive architectures tend to be rather objective as they try to bridge from AI to AGI. And LLM stands for Large Language Model. The most popular large language model is probably ChatGPT right now. Large language models tend to be the products of AI. That is, they're not so much designed using principles of neuroscience as they are trained using big data. In this talk, I want to explore using large language models to try to build a cognitive architecture. Here I have a list of select cognitive architectures that are trying to pursue AGI. There are, of course, many others, but these are just a few. Each of them have demonstrated components of cognition. But in November 2022, ChatGPT-3 came out. It was able to demonstrate far superior cognitive abilities than any of these cognitive architectures. And interestingly, it wasn't even designed with neuroscience and psychology in mind. It was simply trained based on patterns that had been found by scouring the internet and analyzing big data. So this seems to tell us something about what's probably the right way to pursue a cognitive architecture. So let's look a little more closely at the history of how LLMs came about. As you probably know, LLMs are based on artificial neural networks. And artificial neural networks are loosely inspired by the brain. See, the brain is a network of neurons, and these neurons are all connected together by axons and dendrites. So we connect many small computational units together in an artificial neural network, and we train them to interact and affect each other in ways that will hopefully achieve something like cognition. The most popular method for training a large language model, or any neural network for that matter, is called gradient descent. I'm going to represent that with this diagram. Now, usually you'd have far more than two weights in any reasonable neural network, but this diagram only shows W1 and W2, so I can plot it in just 3 dimensions. You'll also need some training data. In this case, we might use the whole internet for our training data. To take a step, we'll draw a mini batch from our training data. So in this case, that might represent just a few web pages. We'll feed, say, the first half of these web pages into our large language model, and we'll ask it to predict the text in the remaining portion of those web pages. The difference between what it predicts and what it actually says is what we'll call the error, and I've plotted that here on this vertical axis. Now, for any possible values of the two weights, W1 and W2, there could be a corresponding artificial neural network that would achieve some amount of error on this particular mini batch. This yellow dot represents the neural network we actually have and the error it actually achieved on this mini batch. Then we perform just a little bit of calculus and we can calculate something called the gradient. The gradient points in the uphill direction on the error surface. What that essentially means is if we adjust the weights in the direction of the gradient, our neural network will always get worse. We don't want our neural network to get worse, we want it to get better. So we actually subtract a tiny learning rate multiplied by this gradient, and that will adjust the weights in a direction that always makes the network just a little bit better with respect to that mini batch. Then we repeat this process in a loop. We essentially step down, 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 downhill until the error is as small as we can make it. And once we do, then we can say our neural network has been trained. In the 2000s or so, neural net researchers were using autoregressive models to do text prediction. An autoregressive model basically consumes all of the input and tries to predict the next word. So for example, if our text says, "I shot the sheriff, but I didn't," we might feed these words into our autoregressive model, and it would try to predict the word shoot. We would then place shoot as the next word in this sequence, feed it all back into the autoregressive model, and try to predict that we didn't shoot the deputy. The biggest problem with autoregressive models is they just didn't really work very well. So naturally, researchers asked themselves, why are humans able to solve this problem? One significant difference is that humans don't consume a whole bunch of text at once. We only read one word at a time, and then we rely on our memories to remember the words we read before. The recurrent model, which I've depicted here, works in this way. It only reads one word at a time, but these horizontal green arrows represent passing and encoding of its memory forward in time. That is, in this case, it will read the word didn't, but it will also accept as an input an encoding of what it remembers reading. That is something that encapsulates "I shot the sheriff, but I." Then it predicts the word shoot, which will append to our input. We'll move on to the next word and repeat until we've predicted the whole sequence. By around 2015, we were using deep neural networks to do sequence-to-sequence predictions. These deep neural networks often contained LSTM blocks. These are a type of recurrent blocks. You can see these green arrows pointing horizontally, indicating that it's passing its memory forward in time. At the time, we thought these models worked rather well, but they were very cumbersome to train. In order to train a deep neural network that contains recurrent blocks, you have to use a technique called backpropagation through time. And backpropagation through time is both cumbersome to implement and it's very slow to actually perform the training. Then in 2017, Google Labs published a paper titled "Attention is All You Need." It introduced a model that they called a transformer. Now the transformer was very similar to the deep neural networks we had been using already, with one significant difference. It replaced those recurrent blocks with multi-head attention blocks. There are two reasons why transformers were heralded as a giant leap forward. First, they achieved significantly better accuracy than the deep neural networks containing LSTM or other recurrent blocks. The second reason is because they got rid of those pesky recurrent connections, so we no longer had to use backpropagation through time. Regular backpropagation is much easier to implement and it's much faster, so we could now make our models scale much better, and that meant we could train them on bigger data. Now, transformers were originally designed for sequence-to-sequence conversion. For example, they could translate from one language to another language. In this case, the left side of this model takes the input language, and the right side of this model outputs the target language, the language that we're translating into. Now, OpenAI was working on a chatbot. They didn't actually need an input language that differed from the output language. So what they did is they cut off the left side of this model, and they only used the right side. Essentially, this returned to being an autoregressive model. We could take the text that was known and feed it in, and it would predict the next word in the text. The big difference is that it still had these multi-head attention blocks, and that turned out to be the great secret that made autoregressive models work. GPT-1 came out in 2018, GPT-2 came out in 2019, but it wasn't until 2022 when ChatGPT-3 came out that people really started to recognize the potential of this model. Now, at the time, ChatGPT was more limited than it is now. It could only accept small input, and it could only produce output with limited size. So there were some researchers that were trying to figure out how to use ChatGPT to write really long text, such as books. The general approach was to create summaries of its own writing. For example, if you were writing a book and you had written chapters 1 and 2, you might then also produce summaries of chapters 1 and 2. Then ChatGPT could consume these summaries to get its context or its mind in the right place before it writes chapter 3. Then hopefully when it writes continuing chapters of this book, it'll stay on topic rather than drift randomly into different areas. As good researchers do, the authors of this paper decided to measure how effective their technique was. So they had some people numerically assess the quality of the writing from ChatGPT. Of course, their expectation was that as it summarized and then reconsumed its own writing, that the overall quality of the writing would gradually decrease. But if it didn't decrease too much, then that would be a publishable result. But instead, something very surprising actually happened. The more ChatGPT iterated on its own writing, the better the writing actually seemed to get. Now you can actually test this surprising result for yourself. To do that, just visit ChatGPT and ask it to write something. After you do, then ask it to critique its own writing. Fortunately, it has no shame. It'll just tear apart its own writing and tell you everything that could be improved with it. And this is where it gets interesting. Then you can ask it to rewrite the original text, taking into account its own criticism. And when you do, it gets better. Now think about that for just a minute. Why would it get better? This is a deterministic machine. Couldn't you just ask it to do its best job the first time? Of course, that doesn't work with students. When we ask them to write a first draft, it's never as good as if they iterate on it a few times. The reason for that's pretty simple. A student can't possibly think about everything that's in their heads. It's too inaccessible. Somewhere in different parts of their minds are different pieces of knowledge and different abilities to take different perspectives on their own writing. In order to utilize all of their knowledge in their writing, they have to perform many iterations. Well, it turns out that large language models are not all that different. They too have many, many parameters. And each of those parameters encodes some component of meaning that it can utilize to produce its writing. So to make a large language model do its best work, it actually turns out it's necessary to give it the opportunity to iterate. In so doing, it can leverage more of its own knowledge to produce better writing. And interestingly, isn't that what being alive is all about? You see, as humans, we're not just given a prompt and asked to produce a knee-jerk reaction, and that's the basis for our entire life. What actually happens is every moment we're consuming more observations. Every moment we're thinking about what's going on, and we're iterating on what's happening in our heads. As we live, we take actions that try to improve our state and improve our situation within the environment, and that in turn feeds back into our own minds. So living itself, or being a cognitive architecture, so to speak, is a very iterative process. Now, to be clear, I'm not trying to take credit for this idea. This actually came from a very brilliant former student of mine. But the idea is pretty simple. We can just compose a prompt for a large language model that enables it to act like a cognitive architecture. For example, suppose you find yourself in situation state, and you want to achieve goal. You observe observations, and suppose you can do any of this list of actions. Which action would you take? Now, this is something we could ask a large language model, and it would pick one of those actions that we gave it as choices. We could also ask it, what would you expect your new state to be after taking that action? And it would produce a representation of what it expects the new state to be. And interestingly, that's exactly what happens within a cognitive architecture. In this diagram, the yellow box represents a cognitive architecture built using a large language model living inside of some environment. It can take actions which will affect its environment, and it can also make observations that tell it about the environment. Now, this state is simply a representation of what's going on in its mind, so to speak. It includes a representation of its environment, its beliefs, what it thinks its goal is, and everything that's important for the cognitive architecture to make decisions. But there are some very interesting properties of this particular cognitive architecture. First of all, notice that it's very, very simple. All of the complexity has been offloaded into the large language model, which achieves its ability to do cognition-like things simply because it was trained on a huge corpus of big data. Second, note that its state will actually be written in English. That's a pretty big deal. Imagine if a psychologist was trying to analyze a human and could simply open up the human's mind and look inside and say, "Oh, I see here that you have trouble with commitment." Or imagine a politician that could somehow open source his own mind. Would you rather vote for the human that may or may not have hidden agendas, or the cognitive architecture that could tell you exactly what it was thinking because its subconscious mind was written in English? Ironically, artificial neural networks are often notorious for being opaque, but in this case they have produced one of the most transparent possible cognitive architectures. Everything it thinks is written right there to be analyzed in plain English. Now, hypothetically, let's suppose we built this cognitive architecture and perhaps employed it controlling a robot that bakes cakes or something like that. Of course, it probably wouldn't be as competent as a human. But interestingly, I claim that we don't need to achieve human-level competence in order to be useful. To illustrate, let's use a car analogy. Long ago, we used to have these self-driving vehicles called horse and buggies. When you drove a horse and a buggy, you didn't actually need to pay very close attention to the road because there was already an intelligent being, the horse, doing it for you. You could just sit back in the buggy and make sure the horse was going in the right direction. Then, of course, cars came along, and a little while later, we eventually got our cars to the point where they were intelligent again and could start following the road for us. Now let's ask a question. When did people start preferring cars over horses? Was it when cars finally achieved parity with the intelligence of a horse? I claim that it was far before then. Cars offer several properties horses don't. For example, they don't require as much space, they don't poop so much, and they're not quite as stinky. Similarly, a cognitive architecture doesn't actually have to achieve parity with humans in order to be useful in a world of humans. For example, suppose we built this cognitive architecture, and perhaps we could employ it controlling a robot that washes dishes or something useful like that. Now, a restaurant owner could easily employ a very experienced person to wash dishes. If he did, he could simply point that person in the direction of the dishes and trust that they would get washed. But that's not what most restaurants actually do. Instead, they tend to hire very unexperienced high school students. Why do they do that? The high school students need far more supervision. They make more mistakes, they break more dishes, they burn themselves more often with the steamer, etc. But there's one significant advantage of high school students. You see, even though they're a lot more work, they work for minimum wage, and that's a significant advantage. Now, suppose that this robot, controlled by our cognitive architecture, wasn't even as intelligent as a high school student. What if it only achieved the cognitive capabilities of, say, a 10-year-old? It would be really painful to teach this thing how to wash dishes. It would make all kinds of mistakes. But it would be willing to work for almost nothing, and it would be willing to work 24/7, wouldn't require benefits. You can see why there's a significant advantage here. And perhaps after going to all the pain of teaching this robot how to wash the dishes, what if it could actually upload components of its intelligence into the cloud? What if the next morning it not only knew how to wash dishes because somebody went through the great pain to teach it, but suddenly it knew how to wait tables, to wipe tables, to flip burgers, and to do other tasks, simply because somebody else went to the pain to teach them? You can't really have that property with humans. But you can with cognitive architecture simply because they are machines. They're encoded in information, and we can make copies of them at will. But there is one really significant limitation of the architecture we've proposed so far. You see, GPT stands for Generative Pre-trained Transformer. Now, being pre-trained means it's not actually learning. It's simply regurgitating the learning that occurred previously when it was pre-trained. So in order to build a cognitive architecture that has the ability to learn, we're going to need to make a few changes. So to do that, let's go back to examining how the brain does it. Let's do a quick comparison of ChatGPT-3 with the brain. ChatGPT-3 has 175 billion weights in 96 layers. They were pre-trained on 1,023 A100 GPUs for 34 days. Now, the reason I'm referring to ChatGPT-3 instead of the more recent versions is because they haven't yet released all of the statistics on the more recent versions. And unfortunately, it looks like they may not be planning to. The complete lack of openness at OpenAI is a pretty concerning property. Now, if we look at the brain, we see that your cerebrum alone has 80 to 100 billion neurons in it. Each of these is distributed in just 6 layers. Now, for a long time, we thought if we could build a model that had 100 billion parameters in it, then it could probably achieve parity with the brain. But as neuroscientists have looked deeper, they've actually found nonlinearities in the dendritic connections themselves. Now, each of these 100 billion neurons is connected on average to about 1,000 others, so this brings us to about 100 trillion synapses. Even our biggest large language models still have a ways to go before they have that many weights in them. But by far the most important property of the human brain is that it can learn. So let's talk about how we could possibly do that in a cognitive architecture. The human brain has a lobe in it called the hippocampus. This is often referred to as our short-term memory. Incidentally, it's approximately the same size and shape as a seahorse. The hippocampus works together with the adjacent entorhinal cortex to track position within space, time, and even conceptual position in whatever you're thinking about. It also seems to be responsible for what you're presently aware of and for aggregating these experiences together. Then when you sleep at night, it seems to use this information as a sort of training data to help form your long-term memories. Now, your long-term memory is encoded in your cerebrum. This is that layer of 80 to 100 billion neurons on the outer surface of your brain. That's the wrinkly layer that you usually think about when you look at a brain. The cerebrum is organized into cortical columns, and these are approximately what I claim is an analog of a large language model, except they're not quite so large. Essentially, you can think of each cortical column as encoding one of your cognitive abilities. For example, if you know how to catch a ball, then you must have a cortical column somewhere in your cerebrum that encodes that ability. The input to the cortical column is essentially the position encoding, or the reference frame. It describes what you're thinking about, or when you're thinking about, or where you're thinking about. And the output of the cortical column is your prediction, or your anticipation of what you expect to observe. For example, if the position encoding specifies something in the past, then the output of the cortical column is your memory. And if the position encoding specifies something in the future, then it's anticipating. It's predicting what you expect to observe. And then based on the difference between what you actually observe and what you expect to observe, this difference becomes an error signal that your brain can use to train its cortical columns. Now, of course, your thinking would be a complete mess if all of your millions of cortical columns all started shouting at the same time. So you have a lobe near the center of your brain called the thalamus. The thalamus's job is essentially to direct or conduct all of your cortical columns. It essentially decides which cortical columns you are currently paying attention to, and is responsible for what we call the stream of consciousness, the thread of thoughts, the topics that your mind is jumping to. This is the reason why humans really only think about one thing at a time, and why they're generally so bad at multitasking. Now, in psychology, there's a model called global workspace theory that's heavily based on this aspect of cognition. It describes each of our cognitive abilities as being sort of an actor on a stage, and the thalamus gets to point a spotlight at the actors that it wants the audience to be paying attention to. And all of the actors that aren't inside the spotlight are what represent your subconscious mind. If they do any thinking without the spotlight pointing at them, these are the thoughts that will seem to pop magically into your head when the thalamus finally gives attention again to those cortical columns. So a very general purpose cognitive architecture may look something like this. Essentially, we take all of the different cognitive abilities that have been developed in computer science, or more especially artificial intelligence, and we treat them as if they are cortical columns, and then we orchestrate them all in a global latent workspace. This would produce something that would truly be a general artificial intelligence, because it would have many different cognitive abilities, and it could apply the appropriate cognitive ability to whatever situation it finds itself in as it tries to live its life. And this brings us to the general cognitive architecture that I'm proposing today. But instead of having a whole bunch of hard-coded or pre-designed computer science components serving as each of the cortical columns, I'm proposing that we could take our large language model-based cognitive architecture and treat it as a cortical column. So in this particular architecture, we have a hippocampus model, which is built using the same cognitive architecture that has a large language model and state. And this would decide which of the cortical columns in the cerebrum model should currently get attention. Now you'll notice I'm using the letters SLM, which stands for Small Language Model. I'm doing this in order to produce something that can be very adaptable and learn very quickly. Because each of these cortical columns is not trying to learn everything it knows like a large language model, but rather specialize on a particular topic, we can use much smaller models for each of the cortical columns, and thus they would be able to learn much more effectively. Because each artificial cortical column in the cerebrum model is very small, it would learn much more quickly than a large language model does. But because there are so many of them working together in an ensemble, the brain as a whole would have the capability of learning all kinds of different cognitive abilities. The outputs of these small language models would then feed into the thalamus model, and the thalamus model would choose which one is relevant for the current situation in order to choose actions for the entire architecture as a whole. I wish I could tell you that I have already built this thing and tested it and could show you my experimental results today, but I haven't quite gotten around to do that yet. So today I'm just sharing my idea and we'll see if it inspires any other ideas. And that brings me to the end of my presentation, so thanks for your attention.